This guide explores Stephen Hawking's The Universe in a Nutshell. Why did Hawking claim that we live in a nutshell? The book's author, Stephen Hawking, is undoubtedly one of the most renowned scientists of our time. His legendary and inspiring life story is universally known and needs no retelling here. It is enough to know that Hawking's primary research areas were black holes and the cosmic singularity, fields to which he made monumental contributions. He held the position of Lucasian Professor of Mathematics at Cambridge University, a chair once occupied by scientific giants like Isaac Newton and Paul Dirac, testifying to his immense academic stature. The Universe in a Nutshell is Hawking's major follow-up to A Brief History of Time. As a publishing phenomenon, A Brief History of Time sold tens of millions of copies and remained on bestseller lists for 4.5 years. In response to fervent reader anticipation, Hawking penned this sequel, which is both more accessible and distinct from its predecessor. The title, The Universe in a Nutshell, is a line from Shakespeare's Hamlet. The character Hamlet says, "I could be bounded in a nutshell and count myself a king of infinite space." For Hawking, this line perfectly mirrored the reality of the cosmos. He believed the history of the universe itself is nutshell-shaped. This might sound perplexing at first, but after this explanation, it will become perfectly clear. In his preface, Hawking notes that A Brief History of Time had a linear structure, with chapters that needed to be read in sequence. The Universe in a Nutshell, however, features chapters that are relatively self-contained. He compares the book to a tree. The first 2 chapters form the trunk, and the rest are branches. Once you understand the trunk, you can explore any branch that interests you. The book's trunk, its first 2 chapters, expounds on Einstein's theory of relativity and Hawking's own model of the universe. Among the subsequent chapters, the one that shares its name with the book, The Universe in a Nutshell, is the most essential. Therefore, we will focus on the core content of these key chapters, following Hawking's line of thought to discover why we live in a nutshell. First, how did Einstein merge space and time into a single entity and give the universe a shape? Second, how did Hawking use mathematics to construct his no-boundary universe model? And finally, building on the first 2 points, we will answer the third question: why did Hawking claim the history of the universe is shaped like a nutshell? Let's begin with the first question. How did Einstein connect space and time to give spacetime a shape? Before the 20th century, our understanding of space and time was intuitive. Both were considered absolute and impervious to any interference. This absolutist view of spacetime was championed by Isaac Newton. He believed that time was like a uniformly flowing river, the same for everyone, while space was an eternal, unchanging, absolute backdrop for all existence. In this view, space and time were independent of each other. Space was 3-dimensional, and time was a separate, single dimension like an infinitely long railway track. However, at the dawn of the 20th century, Einstein's theory of relativity burst onto the scene, completely overturning Newton's absolutist view and giving space and time a new quality: shape. The story begins with our understanding of light. At the time, scientists had discovered that light behaves as a wave and, like sound waves or water waves, presumed it needed a medium to travel through. They called this medium the ether, imagining it as a substance that filled the universe and was absolutely still. The speed of light was thus its speed relative to the ether. This implied that if you measured the speed of light on a moving airplane, it would appear slower when traveling with the light and faster when moving against it. Yet, experimental results showed the exact opposite. Regardless of an observer's state of motion, the measured speed of light was always constant. This discovery, the constancy of the speed of light, led to a revolutionary conclusion: time is not absolute. Imagine you are standing on the ground as a spaceship flies overhead. A person on the ship shines a laser from the tail to the nose. From their perspective, the light travels a distance equal to the length of the ship. But from your perspective on the ground, the ship is moving forward, so the light has to catch up to the advancing nose, traveling a longer distance than the ship's length. Here's the problem. How long did the light travel? Time equals distance divided by speed. Since the speed of light is the same for both you and the person on the ship, but you each observe a different distance, the calculated time must also be different. This means the duration of the same event is not the same for observers in different states of motion. From this, Einstein concluded that there is no single, absolute time, every observer has their own personal time. This theory is known as special relativity. But special relativity wasn't fully compatible with Newton's law of universal gravitation. In relativity, the maximum speed for information transfer is the speed of light, whereas in Newton's theory, gravity's pull is instantaneous. To resolve this contradiction, Einstein proposed the far grander theory of general relativity. General relativity posits that gravity is not a force, but rather the curvature of spacetime caused by massive objects. Earth intends to travel in a straight line through spacetime, but the sun's immense mass warps the spacetime around it, forcing Earth and other planets to follow these curved paths. Hawking uses a famous analogy. Imagine spacetime as a flexible rubber sheet. The sun, Earth, and other celestial bodies are like balls placed on this sheet. When a large ball is placed on the sheet, it creates a depression. When other, smaller balls roll past, their trajectories are altered by this depression. This is the essence of gravity. It also means that the propagation of gravity takes time and cannot exceed the speed of light, thus reconciling it with relativity. With this, the idea of absolute space was also shattered. Space was no longer a static background but a dynamic medium that could be bent and warped, possessing a shape. But this analogy is incomplete. As Hawking points out, it only illustrates the curvature of space. Both relativity and experimental evidence prove that space and time are inextricably linked and cannot be separated. The curvature of space must be accompanied by the curvature of time, meaning time itself also has a shape. To describe this intertwined, twisted form, Hawking likens it to a knot in a rope. Space-time is an inseparable whole. In summary, Einstein first shattered the concept of absolute time with special relativity, then revealed gravity as the curvature of spacetime with general relativity, thereby linking space and time and giving the unified spacetime a shape. Now for the second question. How did Hawking give the history of the universe a shape? Following the birth of relativity, scientists delved deeper into the study of the cosmos. In the 1920s, astronomer Edwin Hubble discovered that the vast majority of galaxies are moving away from each other. This indicated that the universe is expanding, like the surface of a balloon being inflated, where the distance between any 2 points continuously increases. This monumental discovery of cosmic expansion led to a stunning inference. If you rewind time, the universe must shrink. Based on the calculated rate of expansion, going back about 13.8 billion years would cause all the matter and energy in the universe to converge at a single point. This point of infinitely small volume and infinitely large density is called the singularity. Hawking and his colleague Roger Penrose jointly proved that if general relativity is correct, then the universe and time itself must have begun in the Big Bang from this singularity. However, this created a new problem. At the moment of the singularity, all known laws of physics, including general relativity, break down. This meant the origin of the universe was a forbidden zone for scientific inquiry, leaving a space for divine creation. To solve this dilemma, Hawking introduced the mathematical concept of imaginary time and proposed a no-boundary universe model. In this model, the universe is a four-dimensional spherical spacetime without a singularity, and thus without a beginning. Imaginary time is the counterpart to the real time we experience daily. It is a purely mathematical tool related to imaginary numbers. As we know, the square of any real number is non-negative, so negative numbers do not have real square roots. To address this, mathematicians introduced imaginary numbers like $SQRT $1, which are represented on an imaginary number axis perpendicular to the real number axis. Hawking applied this idea to time, calling time measured with imaginary numbers imaginary time. In his mathematical model, the axis representing real time is perpendicular to the axis representing imaginary time. This means the universe's history in real time and its history in imaginary time are like projections of one another, mutually connected. What is the advantage of this mathematical transformation? In Einstein's four-dimensional spacetime, the time dimension is different from the three spatial dimensions we can only travel in one direction, from past to future. But with the introduction of imaginary time, the time dimension becomes mathematically equivalent to the spatial dimensions, effectively becoming a fourth spatial direction. Using imaginary time, Hawking constructed a four-dimensional spherical, no-boundary universe model. We can visualize this unimaginable four-dimensional spacetime by analogy with the two-dimensional surface of the Earth. The Earth's surface is finite, yet it has no boundary or starting point. The South Pole might seem like a beginning, but it is not special. It obeys the same physical laws as any other point on the globe. Similarly, in this model, the universe has no special beginning or singularity. It is entirely self-contained, requiring no creator. Of course, the no-boundary model remains one of Hawking's theoretical proposals and has not yet achieved universal consensus in the scientific community. To recap, by introducing the mathematical tool of imaginary time, Hawking treated the time dimension as equivalent to the spatial dimensions, thereby constructing a closed, self-contained, four-dimensional spherical history for the universe. In this model, the universe has no boundaries and no origin problem to explain. With the groundwork from the first two questions laid, we can finally answer the ultimate question. Why did Hawking say the history of the universe is a nutshell? In his summary of the chapter, The Universe in a Nutshell, Hawking wrote, "The universe has many histories, each determined by a tiny nut." His nutshell theory is a fusion of Einstein's general relativity and physicist Richard Feynman's sum over histories idea. Feynman's sum over histories, or multiple histories, concept comes from quantum mechanics. In the macroscopic world, when a soccer ball is kicked from point A to point B, it follows a single, definite trajectory. But in the microscopic world, the situation is completely different. When a particle travels from A to B, we cannot determine which path it took. Feynman proposed that this is because it simultaneously takes every possible path it might travel in a straight line, go in a loop, or even teleport somewhere else and back again. As bizarre as this sounds, it has been confirmed by numerous experiments. This journey of a particle is its history. Since it takes all possible paths, it has multiple histories. Hawking applied this concept to the entire universe, concluding that the universe too does not have a single history, but rather every possible history. According to Hawking's no-boundary model, the history of the universe in imaginary time is a closed sphere. But according to the multiple histories idea, this sphere could be a perfect four-dimensional sphere, or it could be like a nutshell with a surface full of wrinkles, bumps, and irregularities. So, on what basis did Hawking assert that our universe's history must be nutshell-shaped? Here, he introduced the Anthropic Principle. Its core idea is this: the reason the universe is the way it is that only such a universe could allow for the evolution of intelligent life like us to ask the question, why is the universe this way? The Anthropic Principle may sound like a bit of a cop-out, but Hawking considered it crucial in cosmology. Of the countless possible histories for the universe, the vast majority would be inhospitable to life. For example, why do we happen to live in three spatial dimensions? In a two-dimensional space, a digestive tract would split an organism in two. In four or more spatial dimensions, the law of gravity would be unstable, preventing planets from forming stable orbits, making life impossible. By the same logic, Hawking argued that the history of the universe in imaginary time faced a similar selection process. If the universe's history were a perfect sphere, his calculations showed that its manifestation in real time would be a universe of never-ending, runaway accelerated expansion. In such a universe, matter would never have the chance to condense into galaxies, stars, and planets, and life would certainly never arise. Therefore, the universe we inhabit, one capable of nurturing intelligent life, must have a history in imaginary time that is not perfectly smooth. It must be a slightly distorted, undulating sphere, a nutshell. Such a history, when translated into real time, also begins with a burst of inflation but is followed by a deceleration of expansion, creating the conditions necessary for the formation of stars, planets, and ultimately, life. That is why Hawking said that our universe's history in imaginary time must be a slightly irregular nutshell. And we, just as Hamlet proclaimed, are bounded in a nutshell. Yet we count ourselves kings of infinite space. And so, the essence of the book Why Hawking Says We Live in a Nutshell should now be clear. Let's quickly review. First, Einstein, through his theory of relativity, unified space and time and gave it a bendable shape, overturning the classical view of absolute space and time. Second, to resolve the problem of the universe's origin singularity, Hawking introduced the concept of imaginary time to build a no-boundary universe model, which proposes that the history of the universe is a closed, self-contained, four-dimensional sphere. Finally, by combining Feynman's multiple histories idea with the Anthropic Principle, Hawking argued that the universe has countless possible histories. However, only those histories that are nutshell-shaped, i.e., slightly irregular in imaginary time, could have evolved into the kind of universe we know, one that permits the existence of life. We live in just such a cosmic nutshell, one filled with infinite mystery. That concludes this summary. Congratulations on finishing another book.